Hello. Good afternoon, sir. And good afternoon, everyone. Wish you a warm welcome to everyone, all of the participants on on behalf of our KVPS Institute of Pharmaceutical Education, SWAGH, and Honorable Chairman Dr. Tusharji Randhe and our Honorable Secretary Mr. Nishanji Rande, and from also our institute principal Dr. H.Patil sir. I, Dr. Vikas Patil from Institute of Pharmaceutical Education, BORADI, working as a professor in Pharmaceutical Chemistry Department. Today, our institute organized a webinar on a theoretical and experimental study for FTIR and UV visible spectroscopy techniques. So today and tomorrow, on 2 days of our webinar, we have to invite our today's eminent speaker from the TOSHVIN Analytical, Mumbai. He is a Dr. Girijan. His as a working as a product consultant in TOSHVIN Analytical, Mumbai from last 20 years. Now I will introduce him. He is a product consultant in the field of analytical chemistry with around about the 42 years of experience in analytical chemistry. Also, he is completed his post-graduation from the Kerala University in analytical chemistry. He is also a fellow of Institution of Chemists in India. He is a member of American Chemical Society and lifetime member of Indian Society for the Industrial Chemistry. He worked as in a pharmaceutical as well as in paints as well as in polymer field as in industrial chemistry. Also, he got a approval from the FDA in analysis. Also, he is in Maharashtra of chemical instrumentation analysis. He has extensive experience in chromatographic and spectroscopic analysis. He does a guest lecturing in number of national level institutions at various pharmacy colleges, and he is undergone advanced training in the field of chromatography as well as in spectroscopy. And in also he is as a Thermo Fisher Scientific in UK and Italy, and also at a Shimazu Corporation in Japan, China, and Singapore. Currently, he is working in a TOSHVIN Analytical as a product consultant. So, I welcome Dr. Girijan sir, and I will also thanks for him. He is accept our invitation from our institute as well as from our SWAGH. And now I will give you one announcement for the participants. Questions and doubts, if you have to invited in your comment box, and lastly in live chat you have to post in a comment box. Now I would like to Dr. Girijan sir, you have to start your session for the today's on UV spectroscopy, and tomorrow's we have to continue our FTIR spectroscopy techniques as well as theoretical. Now we also this topic is also as per the PCI regulations. It is a scope to build up the theoretical as well as experimental techniques of UV spectroscopy as well as principal instrumentation. What about the applications of UV spectroscopy? How we have to analyze the drugs as well as the number of scopes and objectives you have to find out from our today's eminent speaker. I hope all the participants we have to get a benefit from the today our eminent speaker. So now I would like to once again thanks for the Dr. Girijan sir. Please accept our invitation from our institute. So you have to start your session, sir.
Okay.
Thank you.
Thank you, Dr. Patil, for giving a wonderful introduction and a very warm welcome to all the participants for the today's session. And I am so happy to be with you this evening, this afternoon, for covering a very wonderful topic, a very, very important analytical topic, analytical technique, which is extremely important in pharmaceutical industry and pharmaceutical students. I will be with you today and tomorrow. As Dr. Patil has already told you, today we are going to cover UV visible spectrophotometry techniques, some of the important applications, especially in pharmaceutical industry. And tomorrow we will continue the session, but we'll be focusing on Fourier transform infrared spectrophotometry, some of the important accessories, and some of the important applications of FDA.
Yes.
So with this, I will I'll start sharing my screen, sir.
Yes, sir. Yes.
Sir, can you see the my slides, sir?
Yes, yes.
Okay.
Yes.
Slide is very clear.
Yes, yes, very clear, sir. Very clear.
Okay. So once again, welcome all the participants for today's webinar session on UV visible spectrophotometry. We are going to discuss very briefly about the basic principles of UV visible spectrophotometry and what are the applications. And toward the end of this session, I will be covering a slide which will show some important accessories that can be used along with the UV visible spectrophotometer. So when we talk about any of these analytical techniques, analytical chemistry, everyone knows, it deals with separation, identification, and quantification of different samples. So analytical chemistry utilizes classical wet chemistry methods and modern instrumental methods. See, we are used to a lot of wet chemistry laboratory methods. I mean, wet chemistry methods are all available in the colleges, college laboratories. They are all important in industry also. And we are not underestimating the importance of classical methods, wet chemistry methods. They are all there. They are all very important. At the same time, today we have got a lot of modern instrumental techniques also. And instrumental methods will include chromatography techniques, spectroscopy techniques, and there are a lot of other material characterization techniques like thermal analysis, and there are a lot of methods for material characterization. So coming to identification techniques, there are so many identification techniques available, and some of the very popular techniques which are used very widely, they include number one, UV visible spectrophotometry, infrared spectrophotometry, atomic absorption spectrophotometry, intensively coupled plasma atomic emission spectrophotometry, fluorescence spectrophotometry are available under identification technique. And UV visible spectrophotometry is the simplest method, the simplest member in this family, which has got wide applications not only in pharmaceutical industry but many different industries and segments. So we talk about electromagnetic spectrum. I hope all the students know what is electromagnetic spectrum. We have today different types of energy available. What white light we see, sunlight we see is also a form of energy. So it's a type of radiation. So we have today different types of radiations available. And each type of radiation has got a characteristic wavelength range. It also has got a characteristic energy content. So there are different radiations available, different wavelength ranges, different energy contents. So we try to arrange all these different types of radiations. See, based on their energy content or based on their wavelength range, we get what is known as an arrangement called electromagnetic spectrum. So now you look at the slide, the electromagnetic what is shown on the slide is a part of electromagnetic spectrum. So if you look at the extreme left-hand side of the spectrum, you'll find some radiations that are having very, very high energy content, like X-ray radiations, gamma radiations, cosmic rays. All these are radiations having extremely high energy content. And if you go to the extreme right-hand side, you will find radiations like microwaves and radio waves. And all these radiations are having extremely low energy content. And everyone knows what is the relation between wavelength and energy. It is an inverse relation. That means when the energy is more, the wavelength is less. Or when the energy is less, wavelength is more. So on the extreme left-hand side of this electromagnetic spectrum, you will have all high energy radiations. And because of the high energy content, the wavelengths are going to be very, very small. And on the extreme right-hand side, you will have high wavelength radiations having very, very low energy content. So our visible light is a part of this spectrum. UV light is a part of the spectrum. Your IR light is a part of the spectrum. They are all members in this family electromagnetic spectrum. Now today we are going to focus on UV visible spectrophotometry. So we should understand what is the working range of UV and what is the working range of visible. Now everyone knows, I think all the students are aware of what is UV spectrophotometer, how does it work. Now if you look at the spectrum, you can see the working range is shown as 200 nanometer to 400 nanometer. The unit of wavelength is given in nanometer. Okay, so that means from 200 to 400 is given as the UV range. And visible range is shown as 400 to 800 nanometer. And beyond 800, you are going to infrared region, near infrared region. That is not a topic of discussion today. We are only focusing on UV visible. And in practical, I think you are having a UV visible spectrophotometer in your laboratory. So if you actually look at a UV visible spectrophotometer, the actual UV recording range is from 190 nanometer to 360 nanometer. Sir, lot of background echo is coming, sir. Lot of background echo is coming. I think somebody's microphone is on, I suppose. Hello?
Yes, sir.
Sir, somebody's microphone is on. There are a lot of background echo. Echo is coming.
Echo.
So please request everyone to put off their microphones.
All participants, you have to request to mute your
Microphones.
microphones.
So in practical, if we talk about UV spectrophotometry, the actual recording range of UV is from 190 nanometer to 360 nanometer. And from 400 nanometer to 800 nanometer, we are in the visible range. We carry out a lot of colorimetric analysis here. Visible range, we normally carry out a lot of colorimetric analysis. The range is from 400 nanometer to 800 nanometer. And UV range is from 190 nanometer to 360 nanometer. Then you may probably ask me what is between 360 nanometer and 400 nanometer. That is basically known as a overlapping region. I will come to that later when we talk about the instrumentation. I will tell you what is that overlapping region from 360 to 400 nanometer. I will tell you about that. Okay. So what we have seen is a part of electromagnetic spectrum. Now we know electromagnetic spectrum is nothing but an arrangement of different types of radiations having different wavelength range and different energy content. Now, this is a very simple thing. Everyone knows about wave-like properties of light. Light, everyone knows, has dual properties. It has got wave-like properties. It has also got particle-like properties. When I talk about wave-like properties of light, the light can propagate through a medium in the form of a transverse wave. You look at the sea, how the water is coming, water waves are coming in the sea. It goes up and comes down, again goes up and comes down. So that's called a wave motion. So the light, similarly, the light also can propagate through a medium in the form of a transverse wave. So when it is propagating like a wave, it has got multiple maximum points and multiple minimum points. All these maximum points are known as crest points, and the minimum points are known as trough points. The distance between two crest points, two consecutive crest points, is called one wavelength, is represented as 1 lambda. So when I say 1 lambda, lambda is the wavelength, that is the distance between two maximum points, consecutive maximum points, and or two minimum points. So that is 1 lambda, that is one wavelength. And this distance can vary from radiation to radiation. If you talk about the radiation like X radiation, this distance will be very small because the wavelength, so this distance is going to be low, is small because of a high energy content. But if you consider a radiation like radio waves, this is going to be very high. This wavelength is going to be very high because the energy content is very low. And we know the universal equation C is equal to nu lambda, where C is the speed of light, nu is the frequency, and lambda is the wavelength. Okay, so that's a very fundamental equation, and these things actually we have already studied in the college. And when that radiation is passing through a medium, propagating through a medium in the form of a transverse wave, it has got certain properties. That means it is responsible for certain phenomena such as transmission, absorption, refraction, and reflection. When I say transmission, the light can get transmitted through a medium. Sometimes when the light is getting transmitted through a medium, a part of the energy can be absorbed by the medium. So we talk about absorption. And the light, when passing from one medium to another medium, sometimes it can undergo refraction. Everyone knows if you are putting a stick into a pond, then you can see the image of the stick is always you can see a bent image. That is basically because the refraction that is taking place, because the light is passing from one medium to another medium having two different refractive indices. Refraction can take place. Similarly, light also can get reflected from a surface. So all these phenomena, like transmission, absorption, refraction, and reflection, all these phenomena are basically connected to a light that is propagating through a medium in the form of a transverse wave. Now, when we talk about spectrophotometry, what are we going to study using a certain spectrophotometry technique? It can be UV visible spectrophotometry technique, it can be infrared spectrophotometry technique, whatever is the type of technique we are talking about. What is it that what we are going to study using a spectrophotometry technique? It's nothing but when a certain radiation, a certain form of light is coming and falling on a molecule, some sort of changes are going to take place in the molecule. And what we are going to study is all these changes that are taking place in the molecule when it is getting exposed to a certain type of radiation. That means when the sample is subjected to a certain radiation, a certain type of light, some changes are going to take place in the sample, in the molecule. And what are these changes? That is what we are going to study. So now the light also, the radiation also can be divided into two types. One is called a low energy radiation and one can be called a high energy radiation, depending upon what is the energy content. Some radiations may be having low energy, so they are called low energy radiations. Some radiations may be having very high energy content, so they are called high energy radiations. Now, if you assume a low energy radiation is coming and falling on a molecule, a sample, let us consider a molecule. I mean, because all samples are all made up of different types of molecules. So when a low energy radiation is coming and falling on a molecule, on a sample, two different types of changes are possible. One is called vibrational changes and one is called the rotational changes. And in spectroscopy term, we call it as vibrational transitions and rotational transitions. Okay. Now, if a high energy radiation is coming and falling on the sample, a totally different type of transition is going to take place, which is called an electronic transition. So depending upon the type of radiation that is coming and falling on the sample, whether it is a low energy radiation or a high energy radiation, the changes that are going to take place in the sample are also different. Low energy radiation causes vibrational changes and rotational changes, whereas high energy radiation causes an electronic change. Now, when we talk about UV visible spectrophotometry, especially UV radiation is a high energy radiation. Now, if you look at if you remember the slide that is the electromagnetic spectrum, UV radiation is always coming on the left-hand side of visible, and visible radiation is coming on the left-hand side of IR radiation. So that means UV has got very high energy content compared to visible range, visible light, and visible light has got high energy content compared to IR light, infrared light. So that means infrared radiation has very low energy content, but UV radiation has got a very high energy content. So UV is always called a high energy radiation, and infrared is always called a low energy radiation. So let us see what type of changes are taking place. So absorption of radiation, suppose you are keeping a sample is getting subjected to a certain type of radiation. And let us see first of all, let us consider a high energy radiation is coming and falling on the sample. What will happen? Electronic transition is going to take place. What is electronic transition? I'm going to tell you, I'm going to show in the next slide. So every sample at normal conditions has got a certain amount of energy associated with that. And this is known as the ground level energy. It is always denoted by E0. So E0 is the total quantity of energy associated with the sample under normal conditions. Now, if this sample is subjected to a high energy radiation like UV radiation, what is going to happen, depending upon the type of sample, the sample will absorb a certain quantity of energy from the incoming UV radiation. As a result, the total energy content of the sample will increase. From E0, it will go to E1. E1 is a high energy level, E0 is the ground level. So that means energy is increasing is going up, is from E0 level, it is going to E1 level. That's called an electronic transition. But why it is called an electronic transition, I'm going to tell you the next slide. So this is actually what is happening in the case of UV. You can see the transition from E0 to E1. This is a UV transition. Now, what will happen if the sample is getting subjected to IR radiation? You can see IR radiation, it's a low energy radiation. So electronic transition will not take place. A low energy radiation cannot induce an electronic transition in a molecule because the energy is the sufficient energy is not there in the radiation because the low energy radiation. What is happening in the case of IR? If the sample is getting subjected to IR, vibrational transition will take place. Vibrational transitions. This we are going to discuss tomorrow in detail. So I am just telling you this. So there are different vibrational levels like V0, V1 like V2 like that, different vibrational levels. So energy can increase from one vibrational, lower vibrational level to a higher vibrational level. But this total energy change is much, much less than the electronic transition. So only vibrational transition you can see they are taking place in the case of IR radiation when the sample is subjected to infrared radiation. Now the last one is microwave. Microwave radiations are having extremely low energy content, and between two vibrational levels there are multiple rotational levels. So there can be some energy changes between these rotational levels, which are of very, very, very low energy content. So depending upon what type of radiation is coming and falling on the sample, there are different types of changes that can take place. So if UV is coming and falling on the sample, electronic transition will take place. If IR radiation is coming and falling on the sample, vibrational transition will take place. And if microwave radiations are coming, rotational transition will take place. Okay. Today we are only concentrating on electronic transition. That is what is happening in the case of UV spectrophotometry. UV radiation, as I told you before, is a high energy radiation. And now look at the slide. Any sample, I told you now, any sample under normal conditions, I got a certain amount of energy associated with that. We normally call it as ground state energy or ground level energy. This is always denoted as E0. And now UV radiation is coming and falling on this sample. Depending upon the type of sample, a certain quantity of energy will be taken by the sample. Then we say the sample is absorbing. Sample is absorbing energy. So a certain quantity of energy will be taken by the sample. As a result, the energy content of the sample will increase because it has already got some energy, that is E0. Now it has received additional energy from the incoming radiation. So what will happen? What will happen? The total energy content is going to increase. So it is going to a higher level from E0 to E1. Now you look at this, E0 is called the ground state energy and E1 is called the excited state of energy. So there is a difference in the energy content. From E0, it is going to E1. So the difference is E1 minus E0 is equal to delta E, or you can call it as H nu. So that means that is the quantum of energy absorbed by the sample from the incoming radiation. Now the question is why it is called electronic transition. Why we are calling it an electronic transition? The reason is you imagine an atom. Atom has got a central nucleus where your protons and neutrons are all there, and around the nucleus in various orbitals, electrons are circling the nucleus. Electrons are actually orbiting in different orbitals. Now, when this is subjected to exposed to UV radiation, and when the sample is absorbing energy, one electron from the outermost orbital gets energized and it is getting elevated to a higher energy level. So since an electron in the outermost orbital is going from a lower energy to a higher energy level, it is called an electronic transition because an electron is getting elevated. And that's the reason we call it as an electronic transition. Okay. So now let us briefly understand what is actually happening. Absorbing species in UV visible. So you are all basically pharmaceutical students. So you must be having a lot of pharmaceutical samples which can be analyzed by UV spectrophotometry. Now you suppose electronic transitions can involve organic compounds, it can involve inorganic compounds, or even sometimes even inorganic complexes. Okay. Now the basic process is M is your sample. We are actually denoting your sample as M. And plus H nu, you can look at what is written on the slide. M plus H nu. That means my sample is subjected to a certain type of radiation. That is, in our case, it is UV radiation. So when this UV radiation is coming and falling on the sample, the molecule M is going to get an additional energy and it is going to an excited level. So M is going to M star. M is the ground level and M star is the excited level. But this M star, which is the excited level, has got a very, very short lifespan. And it is the extent of 10 to the power of minus 8 to 10 to the power of minus 9 seconds. So what will happen? So within a very, very short period of time, this will come back to the normal level. This will come back to the original level, the ground level. So M star will come back to M, and whatever energy is absorbed when it was exposed to the radiation will be given out. It can be given out in the form of heat. It can be given out in the form of fluorescence. It can be given in the form of phosphorescence. There are possibilities. But whatever it is, when the excited state is coming back to the ground state, the energy that's been absorbed by the sample will come out in different forms. So this is one possibility. Okay. Second possibility, the excited level M star, that is your molecule, instead of coming back to the ground level, it can get converted to a totally different entity. M star is getting converted to N. N is a totally different entity. And basically, this is actually what is happening in the case of a photochemical reaction. So there is a possibility that a photochemical reaction also can happen where the excited compound, excited molecule is getting converted to a totally different one. Okay, now when I think these are all, students are all familiar with all this, I mean, energy levels and all. So when you talk about atomic orbital, I mean, there are different orbitals available, molecular orbitals available, sigma orbital, pi orbital, n orbital, pi star orbital, and sigma star orbital. So these are the different orbitals that are available. And out of these sigma and pi and n, they are called occupied levels. And pi star and sigma star, they are called unoccupied levels. So those levels are not occupied. But normal case of sigma and pi, they are all occupied. They're occupied level and unoccupied level. Now, what is so when we talk about an electronic transition, I told you when the sample is subjected to UV radiation, an electron from the outermost orbital is going from a lower energy level to a higher energy level. This is the basic funda you have to remember. Now, from molecular orbital diagram, there are several possible electronic transitions that are possible. And each transition has got a different energy level, different energy content. For example, you see suppose an electron is going from sigma orbital, which is an occupied orbital. Suppose it is jumping from sigma orbital to sigma star orbital. You can see that sigma star transition. These are very, very, very high energy content transitions, and they are actually taking place in saturated hydrocarbons like alkanes. Alkanes means they are saturated hydrocarbons. Very high energy transitions, sigma to sigma star transitions, it will take place somewhere around 140 to 150 nanometer. Our normal UV visible spectrophotometer will not be able to see that because our UV visible spectrophotometer is starting from 190 nanometer. So anything below 190 nanometer, the instrument will not be able to see. So these type of transitions, most of the sigma star transitions that are taking place in the case of alkanes, saturated hydrocarbons, will not be able to observe in our normal UV spectrophotometer because it is actually happening below the lowest range of our equipment. The lowest range of our equipment is 190 nanometer. And these type of transitions are taking place somewhere around 150 nanometer. So we will not be able to see that. Then the second type of transitions is sigma to pi star transitions. Many of these transitions we'll be able to see because that will be mostly in the working range of our equipment so that we can see those transitions. Sigma to pi star transitions. Then there is another transition, pi to pi star transitions. Unsaturated compounds, all these type of transitions we can very well see in our instrument. Unsaturated compound because UV spectrophotometer is very powerful system for unsaturated compounds. So pi star transitions are normally observed in unsaturated compounds, and all these type of transitions can be very well seen in the instrument. Then something called N to sigma star, and they are normally happening in compounds containing oxygen, nitrogen, sulfur, and halogen atoms. And N to pi star transitions, N to pi star, they are also taking place in some of the carbonyl compounds, and some of them we can very well see. So now, if you look at this, sigma star transitions, they are taking place in alkanes, saturated hydrocarbons. And you see where it is written 100, it is happening around 150 nanometer. That's the reason why we are not able to see those type of transitions in our instrument because our instrument is starting from 190 nanometer. So what is an example of an alkane? So for example, you must be using normal hexane. Normal hexane is an excellent solvent for many different types of samples. And if I'm going to use a sample, if I'm going to measure a sample, if I'm going to analyze a sample in UV visible spectrophotometer, I can use normal hexane as a solvent because normal hexane will not interfere in the working range of our equipment. 190 to 360 nanometer, there is practically no absorption for normal hexane. So people say normal hexane is UV transparent sample. That is what we normally say. But in reality, it is not. In reality, it has got an absorbance, but it is happening much, much below the range of our equipment, 150 nanometer. You are not able to see that. So then carbonyl compounds, sigma to pi star carbonyl compounds, many of these are much above 170 nanometers, so that we are able to see all those type of transitions. And pi star transitions are taking place in the case of unsaturated compounds much above 190 nanometer. We can comfortably see all those type of transitions. So that means all those type of samples can be analyzed by UV without any problem. That's the implication. Then N to sigma star, oxygen, nitrogen, sulfur, halogen containing compounds, they're also from 190 nanometer onwards, upwards. Many of them can be seen in our instrument. And N pi star transition that are taking place in carbonyl compounds, we can see all those because they are around somewhere around 300 nanometer, because our instrument is from UV range is from 190 to 360. So we can see all those type of transitions. That means all those type of compounds can be comfortably analyzed by the UV visible spectrophotometer. And this I am just skipping. This is bond formation. I mean, let us skip this. And this is what I've already told you. And now let us come to an important question. I'll ask a very important question to students. I mean, you have got a UV visible spectrophotometer in your laboratory, and you are getting many different types of samples. My simple question is whether all these samples can be analyzed by UV or not. Yes or no? But I know it's an offline, it's an online program, so you'll not be able to answer my question. So I will only answer on your behalf. Not all samples can be analyzed by UV. There are certain samples which cannot be analyzed by UV. Under our normal working conditions, there are certain samples which cannot be analyzed by UV spectrophotometer. Okay, then those type of samples are known as UV transparent samples. So what is the condition? What is the requirement of a sample to be analyzed by UV? Or I can put in a different way, what causes absorption in the UV visible region? I am ask the same question in a different way. Why a sample is absorbing in UV region, UV visible region? So there are certain requirements. Not all samples can absorb. So there are certain requirements. Some samples containing some single bonds, many double bonds. Any sample which contains double bonds will absorb UV. Conjugated double bonds. I hope everyone knows what is conjugated double bond. Single bond, double bond, single bond, double bond type of a configuration. That's a conjugation. Alternate single double arrangement bonding system. So a conjugated bonding system. And conjugated double bonds are highly UV absorbing species. Some metal and inorganic compounds also can absorb UV. Samples containing halogen atoms, nitrogen, oxygen, sulfur, etc. Okay. Now, what causes absorption in the UV visible region? I do not know. You must be aware of. You must have heard of a term called chromophore. And what is a chromophore? I am going to tell you what is a chromophore. A sample molecule should contain at least one chromophore. Then only the sample will absorb UV. Otherwise, the sample will not absorb UV. So, what is a chromophore? Molecules having unsaturated bonds or free non-bonding electrons that can absorb radiation of relatively low energy are called chromophores. Very simple definition. Molecules having unsaturated bonds or free non-bonding electrons that can absorb radiation of relatively low energy are called chromophores. Why we are calling low energy, relatively low energy? Because we know now, you know, as a transition like sigma star. which is happening somewhere around 150 nanometer. That is at a very, very high energy side. We are not able to see that. That's why those type of transitions cannot be monitored by our equipment. So, but the transition should be on the lower energy side, then only we are able to see that. That means 190 nanometer upwards, say 190 to 360, the low energy side, then we will be able to see that. So that is what is written there. Molecules having unsaturated bonds or free non-bonding electrons that can absorb radiation of relatively low energy are called chromophores. Examples include alkenes, it's a double bond system, alkenes, alkynes, ketones, aldehydes, phenyl, and so other aromatic species. A chromophore refers to a functional group that absorbs light, such as C double bond C, C double bond O, N double bond N, N double bond O, and these are all you can consider them as chromophores. So a molecule should contain at least one chromophore. There's a possibility that a molecule may contain more than one chromophore also. In that case, we call it as a multi-chromophoric system. There may be two chromophores, there may be three chromophores, there may be more than four also sometimes. There are those type of compounds are called multi-chromophoric. That means one molecule having multiple chromophores. They all will be highly UV absorbing material. So the requirement is the molecule should contain at least one chromophore. So that's a requirement. Exhibits a characteristic absorption spectrum in the ultraviolet or visible region. And sometimes these chromophores can be in combination. That means multiple chromophoric system is also possible. We will see some one or two examples for that. The next term you should understand is called an oxochrome. If somebody asks you what is an oxochrome, whether an oxochrome is also a group, is also considered, it can be considered as a functional group, but an oxochrome has no absorption in the UV. But what it does is it is acting like a catalyst. It is actually influence the absorption of a chromophore. So oxochromes are influencing the absorption of a chromophore. So an oxochrome is a functional group that does not absorb UV visible in the UV visible region. So by its own, it will not absorb. At the same time, it will influence the absorption because of a chromophore. What it does, it has the effect of shifting the chromophore peaks to longer wavelengths and as well as increasing their intensities. Suppose a sample containing a chromophore has got lambda max around say 225 or 230. And if an oxochrome is there, there's a possibility that the lambda max can get shifted from 230 to 250 or 230 to 260. It can go to longer wavelengths. So that means the lambda max is getting shifted to longer wavelength because of the presence of an oxochrome. That is what an oxochrome does. And one more thing it does, it also increases the intensity of absorption of the chromophore. Suppose the sample containing chromophore has got an absorption value, say 0.5 absorbance. Now, when an oxochrome is there, maybe the intensity of absorption will increase from say 0.5 to 0.6 or 0.5 to 0.7. That means there is an intensity increase. And the increase in intensity and shifting the lambda max towards longer wavelengths can be done by an oxochrome. And some of the examples of an oxochromes are hydroxyl groups, OH group, OR group, NH2 group, thiol group, even some halogens also can act as an oxochrome in a molecule. Now, when you are having, I told about multi-chromophoric system, that means a sample which contains more than one chromophore in the molecule. When a sample contains more than one chromophore, what is the effect on the absorption characteristic? Absorption will go to longer and longer wavelengths. For example, you see a diolefin. I have given different types of compounds. I consider diolefin. Diolefin is having conjugated diolefin having double bonds. Diolefin. It's a two double bonds. Of course, I'm sorry because the double bond is not shown in the compound structure, but it contains a double bond diolefin conjugated. You can see the lambda max is somewhere around 217 nanometer. Now you consider a conjugated triolefin, three double bonds, because each double bond is a chromophore. Diolefin will contain two double bonds, and a triolefin may contain three double bonds. That means the number of double bonds is increasing, and each double bond is a chromophore. So that means the number of chromophore is increasing from diolefin to triolefin. You can see in the case of triolefin, the lambda max is going to 250 nanometer. So that means as the number of chromophores is increasing, the lambda max is getting shifted to longer and longer wavelengths. So that is the effect of multiple chromophores on the molecule. Okay. Now we are coming to an important slide called solvent cutoff. This is very important, especially when you are selecting a solvent for preparing a solution for measurement in UV spectrophotometer. Everyone knows for measurement in the UV spectrophotometer, you have to make a very, very dilute solution of the sample. You have to dissolve the sample in a suitable solvent and make a very dilute solution. Different solvents are available. See here we have shown some solvents like acetonitrile, chloroform, cyclohexane, 1,4-dioxane, even pure water. Different solvents are shown. Now against each solvent, there's a value. Acetonitrile 190 nanometer, chloroform 240 nanometer, isooctane 195 nanometer. So these wavelengths are called cutoff wavelengths, solvent cutoff value. What does it mean? For example, let us take the example of chloroform. Chloroform is a widely used solvent for different types of samples. It's an excellent solvent for different types of samples. Now, chloroform has got a cutoff value 240 nanometer. This simply means above 240 nanometer, the absorption of chloroform will decrease, and below 240 nanometer, the absorption of chloroform will increase. That is why it is known as a cutoff line. Above the cutoff line, absorption is going to reduce, it is going to decrease, and below the cutoff line, absorption is going to increase. So that means if I have to use a solvent for a pharmaceutical sample whose lambda max is 220 nanometer, even though the sample is freely soluble, even though the pharmaceutical drug is freely soluble in chloroform, I will not use chloroform because chloroform has got a cutoff value 240, and now you know below 240 absorption of chloroform will increase, and for your drug sample the lambda max is 220, so chloroform is not a suitable solvent for that. You have to use a solvent whose cutoff is much below that. So I can use acetonitrile. If it is soluble in acetonitrile, 190 nanometer. Aceton, that means practically the entire UV range from 190 nanometer to 360 nanometer acetonitrile solvent is totally transparent. You can use it without any problem. If the sample is water soluble, you can use pure HPLC grade water. 190 nanometer is totally transparent to the entire UV range, 190 to 360. You can use isooctane 195 nanometer, cyclohexane 195 nanometer. So that means you should know what is the lambda max of the sample and know what is the cutoff value of the solvent you are going to use. Otherwise, if you try to use a wrong solvent, the absorbance value that you are going to get for your sample when you make the measurement is going to be it won't be correct. So that is you have to keep in mind while selecting the solvent. Okay. This is an example of a dye sample. It's a water soluble dye. Look at the structure of this material. There are there are 6 different benzene rings in this one. And each benzene ring is a chromophore. Because benzene ring is a conjugated system. It's a 6-membered conjugated ring. And that is so one benzene ring is a chromophore for us. Suppose any sample contains a benzene ring, is an excellent chromophore, and the sample will be definitely having some UV absorption. Now, in this molecule, there are 6 different benzene rings. So that means it's a multi-chromophoric system. And you can expect the absorbance of this material at a very, very long wavelength region. Practically, it goes to visible region. Similarly, so look at the structure of the compound. You will come to know whether the sample has got UV absorbance or not. Tryptophan is a amino acid. I mean, it contains a benzene ring, so definitely it is going to have UV absorption. Okay. If you look at vitamin A, vitamin A is a oil-soluble vitamin. Excellent UV absorption characteristic for this material because of excellent UV absorption characteristic because of multiple conjugation. If somebody's microphone is on, is getting echoed.
No, sir, no.
No, but some echo, some background noise is coming, sir. That's why I told you. Okay. Look at the structure of vitamin A. It's an oil-soluble vitamin. You can see excellent conjugation there. And because of this conjugation, vitamin A is a highly UV absorbing material. Normally, we do the analysis of vitamin A by HPLC using a UV visible spectrophotometric detector. So if you look at the structure of the compound itself, you'll come to know whether the sample will be having UV absorption or not. Okay. Now, this is the spectrum of anthracene. Anthracene is a polyaromatic hydrocarbon. 3 benzene rings are fused together, and each benzene ring is a chromophore. So it's a multi-chromophoric system having conjugation. And then you look at the lambda max, it is almost going beyond 350. That means it is coming very close to your visible region. And that effect is because of multi-chromophoric system. Okay. So, I mean, it's a polyaromatic hydrocarbon example. This is just one slide I want to show you, the students. I mean, there are 4 different effects because of different types of substituents. Sometimes it can be because of certain solvents also. Okay, now we have got a certain sample and we have recorded the spectrum from 200 nanometer up to 600 nanometer, covering both UV and visible. And if you look at the spectrum, you will understand the lambda max is somewhere very close to 400 nanometer. That's the lambda max, somewhere around 400 nanometer. Now there are 4 different types of effects that are possible. One is known as I'll tell you what are those: hyperchromic effect, hypochromic effect, betachromic effect, and hypsochromic effect. So let us see the first 2: hyperchromic and hypochromic. Now this material has got a lambda max somewhere around 400 nanometer, and it has got absorbance approximately somewhere around 0.7 absorbance, because your y-axis is your absorbance scale. Normally we have a scale of 0 to 1. So if you consider say 0 to 1 scale, this compound, you can consider approximately 0.7 is the absorbance value. Now, if I am connecting a certain attachment on this molecule, you can see the upward arrow, hyperchromic effect. That means the intensity of absorption is increasing. Say from 0.7, it is going to 0.8. At the same time, wavelength is not changing. Wavelength is at same place, 400 nanometer. Lambda max is at the same place. But intensity of absorption is increasing. That is what is known as a hyperchromic effect. So hyperchromic effect is the effect because of a certain substituent wherein the absorption intensity is increasing without changing the lambda max. That is called hyperchromic effect. And reverse of this can also possible. Exactly opposite also is possible. That is called hypochromic. In that case, what will happen? The intensity of absorption will decrease. From 0.7, it will come to 0.6 or 0.5. Intensity is coming down. At the same time, lambda max is not changing. That is called hypochromic. So one is an upward arrow, one is a downward arrow. Hypochromic. Reduction in intensity and upward arrow is increase in intensity. Lambda max is same, no change. Then the other 2, one is called betachromic and one is called hypsochromic. So it is the opposite of what now we discussed. In this case, what will happen? In the case of betachromic, is also known as a red shift. the lambda max is changing. It is actually going to longer wavelengths. At the same time, your intensity will not change. Intensity is going to remain at the same level. If we consider it as 0.7, it is going to remain at 0.7 level. At the same time, your lambda max is changing. Say from 400, it can go to 500 nanometer, longer wavelength. So any shift towards longer wavelength is normally called as a redshift in UV. Redshift. Redshift means shift towards longer wavelengths. Okay, so in this case, what will happen? Bathochromic shift, your lambda max is changing to a longer wavelength. If it was originally 400, now it may be 500. At the same time, your intensity is not changing. And the reverse of this, that is known as a hypsochromic effect or a blue shift. In this case, what will happen? The lambda max will change, it will come down. It will get shifted towards lower wavelength. Say from 400, it will come to say 300. It is coming to higher energy side, lower wavelength side. And any shift towards a lower wavelength side is called a blue shift. At the same time, your intensity is going to remain same. So these are the 4 different types of substituents effect that are possible. Hyperchromic and hypochromic, where intensity of absorption can either increase or decrease without change in the lambda max. And bathochromic and hypsochromic, where the lambda max can change either to longer wavelength or shorter wavelength without change in the intensity of absorption. So this is sometimes even a sample when you are dissolving a certain solvent. Yes, sometimes you may even find a shift in the lambda max values. 2 different solvents, maybe because the effect of this is the effect of a solvent also sometimes. So some substituents or solvents also can cause these type of changes in the lambda max value as well as the intensity of absorption value. Now let us consider UV visible spectrophotometry. Most of you must be doing quantitative analysis. Most of the time, we use UV visible spectrophotometer as a quantitative analytical technique. We normally don't use UV visible spectrophotometry as a qualitative analytical technique. There is a reason we are going to see that. So normally it is used for quantitation. And everyone knows you have to make a very dilute solution of your sample in a suitable solvent. And you have to fill a cell. That cell is known as cuvette. And the cuvette can be of different types. It can be made of glass. It can be made of quartz. It can be made of plastic. There are different types of cuvettes available. The standard cuvette is actually 1 centimeter by 1 centimeter square set. And you have to fill the cuvette with your solution. Approximately around 75% of the total volume is more than sufficient. And the cuvette has got 2 transparent sides and 2 semi-transparent sides. So never try to touch the transparent sides with a finger. You have to always hold the cuvette on the semi-transparent side. And if anything is sticking to the transparent side, you have to just wipe it with a tissue paper and keep this cuvette along with the solution in the sample compartment, and then you can read the absorbance value on the equipment. So when you are keeping the sample solution in the cuvette in the sample compartment, what is happening? The light from the light source is coming and falling on the sample, and depending upon the sample, a certain amount of energy will be absorbed by the sample depending upon the concentration, and then the remaining is coming out. That is called the transmitted light. So incident light intensity is I0, transmitted light intensity is I1. Transmitted light intensity will be always less than the incident light. So I1 by I0 is equal to T. That's a transmittance value. T is equal to I1 by I0. And if you multiply this I1 by I0 by 100 into 100, you'll get percentage transmittance. We normally sometimes we talk about 85% transmittance, 90% transmittance and all. Okay. And there are 2 laws. The laws of spectrophotometry. Whenever you want to use a spectrophotometer for a quantitative analysis, there are certain laws governing that. And what are the 2 laws governing the quantitative analysis? One is called Lambert's law. Lambert's law says absorbance is directly proportional to the path length. What is the path length? Path length is nothing but your your cuvette is made of whatever is the material. It has got the standard cuvette is 1 centimeter by 1 centimeter square. So 1 centimeter is the path length. So there are different path length cuvettes available. So standard path length is always 1 centimeter. So absorbance is directly proportional to path length. That is what is known as Lambert's law. And what about Beer's law? Beer's law says absorbance is directly proportional to concentration. Now, if we combine these two, Lambert's law and Beer's law, we get what is known as Beer-Lambert law, where we can say absorbance, capital A, is directly proportional to the concentration and the path length. And that is what is basically known as Beer-Lambert's law. Okay. And this is the equation. A is equal to epsilon multiplied by L multiplied by D. A is the capital A is the absorbance value. That is what you are getting from the instrument. Epsilon is called molar absorptivity. That's a constant for a given sample. L is the path length. Well, you are going to use the same cuvette for your standard as the samples. Your path length is always constant. 1 centimeter, it is same for standard and sample. So that's also a constant. So what is the variable? Variable is only C, that is your concentration. So we can say absorbance is directly proportional to concentration. Ultimately, your Beer-Lambert's law comes down to that. Absorbance is directly proportional to concentration. That means your concentration is high, your absorbance value is going to be high. And if your concentration is low, your absorbance value is going to be low. Okay. And this is what the same thing what is shown. And limitation of Beer-Lambert. So you should see this. You have to always prepare a very dilute solution. If your solution concentration is more than 0.01 molar, deviation from linearity can occur. And if linearity is lost, then your actual analysis result will not be correct. Because when you are actually making a quantitative analysis, you have to plot a calibration curve. And we will be preparing 3 different concentrations, 4 different concentrations, or 5 different concentrations to create a calibration curve. This is known as 3-point calibration, 4-point calibration, or 5-point calibration like that. All the calibration points should lie on the same line. That is called a linear line. Nothing should go out of that. Then becomes non-linear. Okay, if the non-linearity comes, your analysis result will not be correct. So deviation can occur if your concentration size is more than 0.01. So this is a very important point you have to consider. You have to prepare always a very, very dilute solution so that your absorbance value lies between 0.3 to 0.8. This is the normal advice we give to the users. Your absorbance value should lie between 0.3 to 0.8. If it's more than 0.8, you can dilute slightly with the solvent so that it comes below 0.8. And if it is less than 0.3, that means your sample solution is too dilute. You may have to add a little more sample quantity. So adjust your concentration of solution in such a way that your absorbance value is between 0.3 and 0.8. Okay, stay late, I'm just leaving. And let's come to some other pharmaceutical analysis where UV spectroscopy is very, very widely used. Applications in pharmaceutical analysis. A robust workhorse method for the quantification of drugs in formulations where there is no interference from excipients. Okay, you will be having a lot of pharmaceutical formulations. Active drug is API is there and a lot of excipients are also there. And excipients should not interfere in the analysis of your API. In that case, UV is an excellent technique for the quantification of API in the formulation. Determination of pK values of some drugs. You can use UV for that. Determination of partition coefficients and solubilities of drugs. Used to determine the release of drugs from formulations with time, that is in dissolution testing. Very important application in pharmaceutical industry. Dissolution testing where UV is very widely used. Then UV spectrum of a drug is often used as one of a number of pharmacopoeial identity. Many times, even as per the pharmacopoeial methods also, from the absorption maximum also that can be used as a identity check also. Now, what are the strengths of UV spectroscopy? An easy to use, cheap and robust method. Very easy technique. UV is not at all a complicated analytical technique. Very easy to use, and affordable price also is not so costly, and a very robust system. And you can use it for quantitative measurements of drugs in formulations. Okay, routine method for determining some of the physicochemical properties of drugs. Some of the problems of the basic method can be solved by the use of derivative spectra. Limitations, only moderately selective. That means you are going to see one or two slides going forward. You are many of the main problem with UV. You cannot use it as a qualitative analytical technique because many compounds will offer you, will give you very, very similar type of spectra. That's the main drawback with UV. That's the reason why today we are not using UV as a qualitative analytical technique. At the same time, it's a wonderful quantitative analytical technique and not readily applicable to the analysis of mixtures. If different compounds or different drugs are mixed together, then you also may be a problem because there can be a lot of interference because of very close lambda max values. See, for example, you look at the UV spectrum of betamethasone and hydrocortisone, two different steroid compounds. Both are two different compounds, but you look at the UV spectra, both are more or less similar. I'm not telling 100% similar, but more or less similar. There is not much of a difference between the even the lambda max value also. You can see they are providing you very, very similar spectrum, even though compounds are different. One is hydrocortisone, one is betamethasone. So there is a very close similarity. So that means by using a UV spectrum, you will not be able to differentiate one compound from another compound. That's a major drawback with UV. And that is why today it is not a popular qualitative analytical technique. See, some of the absorption maxima, some of the corticosteroids, hydrocortisone, betamethasone, clobetasol butyrate, betamethasone sodium phosphate, you can see the lambda max values 240, 240, 236, 241. That means they are very, very close. Lambda max values are very close. That means you will not be able to differentiate. For example, hydrocortisone and betamethasone, both are having lambda max at 240. Betamethasone sodium phosphate and betamethasone 240 and 241. Not possible for us to differentiate. So that can be a major drawback with the UV. Similarly, UV spectrum of procaine under acidic conditions and basic conditions. Okay, the spectrum, the intensity of absorption may be different, but the overall spectrum, there can be slight changes. So in the acidic condition, basic conditions, they are offering two different spectra with difference in the intensity of absorption. Similarly, also phenylephrine under acidic conditions and basic conditions, there's a slight change in the lambda max values, not a major change. Okay, both are, there is going to be a slight change in this thing. So the overall, the spectra is going to be different for a drug under acidic conditions and basic conditions. Assay of penicillins by derivatives. Sometimes some drugs are to be derivatized. They cannot be directly analyzed by UV, maybe because of lack of a chromophore. A British Pharmacopoeia utilized the formation of a derivative in order to quantify penicillins in a formulation. But the reason is some of the penicillins do not have a very distinctive chromophore. And because of the lack of chromophore, they will not absorb UV. So you may have to chemically derivatize the compound and convert it to a different entity which has got sufficient UV absorption so that you can measure the sample in UV. So using the formation of a complex with mercuric ion in presence of imidazole as a catalyst, a derivative of penicillin is produced which has got an absorption maximum between 325 and 345 nanometer. So by converting penicillin into a derivative by reaction mercuric ion in presence of imidazole, you can get a derivative which has got a lambda max somewhere around 325, between 325 and 345. So this assay method is used by BP method for the analysis of preparations containing ampicillin, amoxicillin, cloxacillin, flucloxacillin, etc. And this is the actual the reaction ampicillin with imidazole and mercury chloride, and you are getting a complex which has got a lambda max number around 325 nanometer. Protein melting temperature. Protein, the absorbance spectra of proteins result largely from the presence of aromatic amino acids. There are amino acids like tryptophan, tyrosine, and phenylalanine. And because of these presence of these amino acids, proteins have got UV absorption. A protein at room temperature has a very specific tertiary structure that creates a specific electronic environment for the aromatic amino acids. So when the protein is heated, you prepare a protein solution when it is heated, as the temperature increases, at a certain temperature, it will unfold, the structure will unfold, or we can say the protein starts melting. And when it is melting, it is going to lose its structure. And when it is losing the structure, the electronic environment of the aromatic amino acids also will change, which will result in specific absorption. Okay, so that is what. So we can use even the UV for protein estimations. There are certain standard methods available in the software. Nucleic acid melting temperature. Deoxyribonucleic acid (DNA) in normal state, it comprises of two strands of deoxyribose nucleus, helically bound, like two strings are helically bound around the same axis. Okay, now these two strings or strands are linked by hydrogen bonds between the purine and pyrimidine bases. Adenine is joined to thymine and guanine is joined to cytosine. So there is a AT structure, AT connection and a GC connection. Adenine, thymine connection and guanine, cytosine. So that is how that hydrogen bonds are formed and these strings are actually helically bound. And these bases are primarily responsible for UV absorptions of DNA with a peak maximum at 260 nanometer. Okay. So as in any multi-component system, when you are observing the absorbance of a DNA molecule, and the absorbance of a DNA molecule is because of the sum total of the individual absorbances. Because each one is going to absorb. There is an absorbance because of adenine, absorbance because of guanine, because of cytosine, and because of thymine. And all these put together, A adenine plus A guanine plus A cytosine plus A thymine, that will give the total absorbance of the DNA molecule. Okay. However, the absorbed absorbance is always significantly less than the expected because the hydrogen bonding between the bases changes their electronic environment. So when a molecule is heated, the hydrogen bonds are going to break and the double helix unwinds. The structure will be lost, the helical structure will be lost, and then the absorption will increase. Okay. So nucleic acid melting temperature, very, very important information for the biotechnologist or the biological chemist. This is called the denaturation process. That means when you are heating the DNA solution, the helical structure is going to be unfold. And that is called as a denaturation process, or it is also known as the melting of DNA. So in a DNA melting experiment, the temperature of DNA solution is increased in a stepwise fashion, and the absorbance at 260 nanometer at each temperature is measured and plotted as a melting curve. So we are going to keep the lambda max same, 260 nanometer wavelength we are going to fix. And then we are going to increase the temperature of the solution. At each temperature, what is the absorbance value at 260 nanometer? That is what is measured by the equipment. And then it is plotted. And then we get a melting curve. The midpoint of the temperature range. So we have absorbance values at various temperatures at a fixed wavelength 260 nanometer. The midpoint of the temperature range over which the melting occurs is the Tm value. So the midpoint of the curve is called the Tm value, or known as the melting temperature value. The Tm value of a particular DNA sample depends primarily. So different types of DNA molecules will be having different Tm values because the Tm value of a particular DNA sample depends primarily on the percentage of GC pair in the sample, each of which contains 3 hydrogen bonds, as against each of 80 pair, which contains only 2 hydrogen bonds. So different DNA structures may be having different GC pair and different AT pair. So depending upon that, their melting temperature also will be different. So by precisely finding out what is the melting temperature of DNA molecule, then the biotechnology will get more information as to what can be the structure of the DNA molecule. Okay. The higher the percentage of GC pair in the sample, the higher the observed melting temperature. Enzyme characteristics, I am not going into details. Let us come to UV spectroscopy, some basic components. I mean, all students, I hope they are all familiar with UV experiment and UV spectrophotometer instrument. They must have seen the instrument. We have a light source inside the system. And we have got 2 different light sources because we say UV visible spectrophotometer. So there is a light source for UV range. There is a light source for visible range. And we'll see what are those light sources that we are going to see. So whatever is the source we are going to use, the light is coming out of that. The light that is coming out of the source is called a polychromatic light. Polychromatic light means a light which contains multiple wavelengths. They are not a polychromatic light. And this polychromatic light is to be converted to monochromatic light. Monochromatic light means a light having a single wavelength. Polychromatic means light having multiple wavelengths. So originally the light coming from the source is polychromatic, and that will be passing through a monochromator. And this monochromator is converting this polychromatic light into a monochromatic light. So that's the job of a monochromator. It is converting a polychromatic light into a monochromatic light. So what is coming out of the monochromator will be having a single wavelength. That's called a monochromatic light. And that monochromatic light will be passing through our sample solution, what we have taken in the cuvette and kept in the sample compartment. Our sample is a pharmaceutical drug sample. That monochromatic light will be passing through the sample compartment. And then depending upon the concentration of the sample, there will be some absorption. Whatever is coming out of the sample compartment will go to the detector. Detector is going to give a signal, and that signal will be recorded. That is going to be your output. And what you get from here is a UV spectrum. Okay. So these are the main parts of a UV visible instrument. Number 1 is the source, the light source. Whether it is a UV source or a visible source, first we should have a source of light. And second thing is a wavelength selector. Wavelength selector is nothing like a monochromator. Once upon a time we were using filters, but filters have become outdated now. Nowadays we are using monochromator. And now you know why a monochromator is required, because a polychromatic light is to be converted to a monochromatic light. That's why we are using a monochromator. And whatever is coming from the monochromator is passing through the sample container. That's the sample compartment. That's your sample cuvette. And whatever is coming out of the sample cuvette is going to the detector and your readout devices. I mean, your PC and your recorder, a printer, all those. And either your instrument can be a single beam instrument or a double beam instrument. And you also should understand what the difference between a single beam equipment and double beam equipment. I am going to show you some slides after some time. This is also very, very important. Okay. Now, source of light. Now, upon it's a continuous source. Sources used in UV visible spectrophotometers are continuous sources. Okay, now there are certain line sources and all, not in UV and this thing. We are using a continuous source. Okay. Suppose you are working in visible range or NIR range, near IR range. Our lamp is, the source is a different one. It's called a tungsten lamp. We are using a tungsten halogen lamp in the visible region. It also can be used in NIR region, visible region. So it can start from 320 nanometer. That's a range. It can start from 320 nanometer. It can go to 2500 or even more than 2500 nanometer. Now, if you are looking at the ultraviolet side, UV side, then our lamp is different. lamp is known as a D2 lamp, or it is known as a deuterium lamp. And deuterium lamp can work from 190 nanometer, and it can even go to 360 nanometer. Here it is written 400 nanometer. I mean, if you look at the slide, you can see 400 nanometer. Now I am coming to a point which I told you at the beginning. Because I told you when I started my lecture, I told you the UV is from 190 nanometer to 360 nanometer. Visible is from 400 nanometer to 800 nanometer. Then probably you may ask, what is the region between 360 to 400? And I used a term that time called a overlapping region. Overlapping region is nothing but between this 360 nanometer and 400 nanometer, the lamp will change. Suppose you are going from, we are coming from visible to UV, tungsten halogen lamp will be automatically put off, and your deuterium lamp will be switched on. So the change of lamp is actually taking place. Say a UV lamp is changing over to visible lamp, or a visible lamp is changing over to UV lamp. And that change is actually taking place between 360 and 400. That's why it's known as a changeover region. So that is the reason why it's not a changeover region. So normally your deuterium lamp, you can work from 190 nanometer to 360 nanometer. That is why we are always recording the UV spectrum. Probably if you are doing some experiments in your laboratory, when you are recording the UV spectrum, you are recording between 360 nanometer and 190 nanometer. That's a normal recording range of a UV spectrum. And wavelength selector, whatever is coming from the source, as I told you, it's a polychromatic light having multiple wavelengths. They have to be converted to the monochromatic light. That means light having a single wavelength. And this is to be done by a wavelength selector. Once upon a time, we were using filters. But filters are no more used because they are outdated, because their efficiency is very low. So today we are using a monochromator. Monochromators are very, very powerful wavelength selectors. That means a monochromator can convert a polychromatic light into monochromatic light without any problem. So, for example, suppose tomorrow you are having your professor is giving a sample, a pharmaceutical sample, and that is to be analyzed by UV spectrophotometer, and the lambda max of the sample is 254 nanometer. Lambda max of the sample is 254 nanometer, and you are going to do a quantitative analysis. So you have to make the measurement at 254 nanometer only. Okay. Now, when you switch on the instrument, D2 lamp will be on. From D2 lamp, the radiation will come, but that will contain so many other wavelengths other than 254. Right from 190 nanometer to 360 nanometer, there are so many wavelengths. And just one among them, 254 is also there. There are multiple wavelengths are there. Okay. Now, when this light is passing the monochromator, and if you have selected 254 nanometer in your software, only that 254 nanometer wavelength will be given out by the monochromator, and that 254 nanometer wavelength radiation will pass to a sample compartment so that you can carry out your quantitative analysis. Okay, so that's the importance of, that's basically the responsibility of the monochromator, conversion of polychromatic light into a monochromatic light. Okay, so you can see this is something, this is a monochromator. I'm not going into too much of hardware system, hardware details. So they are used for spectral scanning, varying wavelength of radiation over a considerable range. We say scanning. We say from 360 nanometer to 190 nanometer, I'm going to scan. Now, for example, I will tell you the importance of scanning. Suppose, as I told you, you got a sample, and your professor has told you this sample has got a lambda max at 254. Your job is very easy. You have to only set your lambda max as 254 nanometer in the software, make a solution, and find the absorbance value. It's called a photometric method. Very simple quantitative analysis. But suppose you don't know what is the lambda max of sample. You do not know whether it is 254 or 230 or 290 or 300. You do not know. In that case, what you have to do, you have to make a scan from 360 nanometer to 190 nanometer, and find out where is the lambda max coming. Lambda max is nothing but the wavelength at which you are getting maximum absorption value. That is lambda max. So you have to make a scan from 360 nanometer to 190 nanometer and find out the lambda max for your sample first. And for that, you are doing a scanning. So that is the scan mode is that the software. So you have to go to a scan mode, scan the sample from 360 to 190, find out the lambda max where you are getting, come back to photometric mode, keep that lambda max, and then do the quantitative analysis. So that is how, if you don't know the lambda max, you have to find out by carrying out a scan. Okay. Now the monochromator is basically used in UV visible region, and there are different types of monochromators and different hardware structure and other things. I mean, design and other things. We are not going into those details. But a very, very common monochromator is what is shown here. It's called a very, very powerful monochromator. And this monochromator, monochromator is nothing but you can say it uses a grating, diffraction grating. Grating is nothing but maybe a glass plate over which a thin film of aluminum is coated, vacuum coated. And over this surface, we are actually drawing grooves. We are actually drawing lines. Line in the sense 1 millimeter distance. Sometimes we are drawing 1,200, 1,600 or even 1,800 lines in 1 millimeter distance. Can imagine in 1 millimeter distance, we are drawing 1600, 1800 lines. It is all drawn by laser. More number of lines we are drawing, more efficient will be the grating. And this grating is actually mounted on a turntable, which is motorized. And that's your monochromator. And when the light is coming and falling on this, and this grating can actually move, and because it has a motorized platform. And suppose you have selected a certain wavelength for your sample, say 254 nanometer wavelength, you have already selected in the software, the grating will move in such a way at a certain angle, only 254 nanometer wavelength light will come out of that. That is how we try to select it. That is how the monochromator works and gives you the required wavelength which has to pass through your sample solution for your quantitative estimation. Okay. We can see some more applications of UV visible NIR spectroscopy and why we cannot use, what are the advantages of UV visible spectroscopy. For example, whatever sample you are going to keep, for every sample there is a spectrum that is available. Easy sample concentration calculations because you have got a very user-friendly software. Sample concentration, they are all automatic calculations, no manual calculations involved, and affordable instrumentation. The instrument is also not very costly. So that is the reason why today every educational institution, even a college or even a school laboratory also can afford to buy a UV spectrophotometer. The price is not very high. Normal case. Well, of course, we have also got very, very high priced UV, but that is not normally for, that's only for some very advanced research and some research laboratories and other things. Otherwise, normal, even industry also, UV is considered as a very affordable instrument. It's not a very high priced system. And what are some of the limitations of UV? I mean, we say disadvantage, or better to use the term limitations. Little structural information, very similar spectra. I told you when we are talking about hydrocortisone and beta-methasone, and you saw the spectra also, they're very, very similar. Even though there are two different steroids, the spectra are not totally very different. They're very similar. That is actually what happens in the case of UV. Whatever sample you keep, most of the time, you get very, very similar spectra. That is a major limitation of UV. That means if I am giving you two different compounds, A and B, and if you record the spectrum of A and spectrum of B in a UV spectrophotometer, more or less, most of the time, these spectra will be more or less identical. That means looking at the spectrum, you'll not be able to differentiate compound A from compound B. That's a major limitation of UV. That's the reason why today we are not using UV spectrophotometer as a qualitative technique. It is used only as a quantitative analytical technique. Whereas when we talk about IR tomorrow, it is predominantly a qualitative technique because these two compounds A and B, if I record an IR spectrum of A and IR spectrum of B, they will be totally different. So I can differentiate A from compound A from compound B by looking at IR spectrum, which is not possible in the case of UV. So that's a major limitation. But at the same time, please understand UV is a very well accepted, very important quantitative analytical technique, and which is used in every walk of industry. Not only industry, academics, wherever you are. I mean, when you go to a laboratory, you will find at least one UV visible spectrophotometer. Let us see some agricultural applications. In the case of food industry, color and consistency are very important. Color of the food product, consistency of the food product are very important factors. And you have to control from batch to batch. Variation should not take place either in the case of color or in the case of consistency. And many times you are adding lot of small amounts of different chemicals in the food formulation. They're all additives, maybe antioxidants, anticoagulants, anti-settling agents, dispersing agents, the different types of chemicals like benzoic acid, sodium nitrite, they're preservatives and all that. They're added in very small concentration, and they have to be very precisely quantified also, because their concentration should not exceed certain limits. So we have to precisely quantify these additives that are added to the food formulation, and for that you can use UV. UV is widely used. Similarly, color of the food product. Color is also a very appealing factor. So we have certain color measurement software that can be used along with the system, so the color also can be controlled from batch to batch. Very important applications in food industry. Similarly, beverage industry, liquor industry, beer manufacturing, all these places also. I mean, color is a important factor. Some of the additives that we are going to add in these formulations, they are all very important. And so UV is very widely used in beverage industry also, beverage and liquor industry also. Leaf analysis, chlorophyll and photosynthesis project, purely an academic interest, academic application, because everyone knows chlorophyll has got a very dark green color. So depending upon the chlorophyll content, the color also can change. So we can actually estimate from the color intensity, we can actually estimate the chlorophyll content. It is purely an academic application, not an industrial application. Biological application, we have already discussed about protein analysis. There are different methods available for protein analysis, Lowry method, BCM method, CBV method, Biuret method. Different methods are available for protein. These are all biotechnological applications or biological applications. And DNA, RNA analysis, I told you we are measuring the absorbance at various temperatures at 260 nanometer. Similarly, one kinetics, monitor rate of reaction and enzymatic reaction, we can use UV. In the software itself, there is a provision for that. There's a standard feature, kinetic feature is there in the software, so that we can actually find out monitor the rate of reaction. And enzymes also can be evaluated. Enzymes cannot be directly evaluated, but enzymes can be evaluated only by the rate of reaction which is catalyzing. So that also we can do by UV. And industrial applications, number one is pharmaceutical industry, pharmaceutical manufacturing. Every pharmaceutical industry, every pharmaceutical company will have at least a UV. And big companies will be having multiple number of UVs there. Because there are right from raw material analysis, intermediate analysis, your dissolution testing, content uniformity, cleaning validation in API manufacturing, plenty of areas where we are using UV. And so UV is a 100% must instrument in the pharmaceutical industry. And if you go to some big companies, you can see multiple UVs used for dissolution testing. Dissolution testing of your pharmaceutical students, you know what is dissolution testing. So UV is a very important required equipment for dissolution testing. We can similarly use it for cleaning validation. We can use it for content uniformity testing, raw material analysis, intermediates, all these where we have got plenty of applications for UV. Similarly, in the chemical manufacturing also, quality control, raw materials, intermediates, kinetics, lot of areas where we can use UV. Academic and government application, environmental testing, sometimes contaminants in streams and wastewater can be tested by UV. We have a slide coming for that. I will tell you more about this. And research in institutions, CSIR laboratories and research institutions or big universities, a lot of research activities are going on optical materials. So when you are working on optical materials, they are more concerned with the reflection and transmission properties and the film thickness, thin films. So we have different attachments, we have different accessories for all these type of activities. They are purely academic activities, academic research. Similarly, for students also in colleges and universities, students must be having their own projects and all, so they can use a UV for their project work. So it's widely applicable in academic as well as government applications. Coming to what type of samples we can use in the case of UV, only liquids and solids, no gas analysis is possible in the case of UV. But when we talk about IR tomorrow, IR can handle all the three types of samples: gas sample, liquid sample, and solid samples. In the case of UV, it is only liquid and solid. And in the case of liquid, we can divide this liquid to three different types. One is called a transparent liquid, one is called a translucent or turbid liquid, and one is called an opaque liquid. Transparent liquid means, say for example, if you take acetone, you take methanol, you take pure water, they're all transparent samples. Benzene, I mean anything, transparent, totally transparent samples. And for these type of samples, you can directly keep the sample cuvette in the sample compartment, and you can measure the transmittance value. You don't require any special attachment, nothing. You can directly keep the sample, fill the sample cuvette to the sample, and keep it in the sample compartment. You can read the transmittance value. So measured by transmittance method, no accessories required. Suppose your liquid sample is a turbid sample. It is not a clear sample. It is turbid. Lot of suspended materials. It's a turbid sample. It's not very clear. In that case, direct transmission measurement is not possible. You have to use an attachment for this. And that attachment is known as an integrating sphere. It's an accessory. So you have to purchase this accessory and use it along with your UV spectrophotometer. Then you can analyze a turbid sample, and then you can make a transmittance measurement or reflectance measurement, provided you have this accessory. If that accessory is not there, integrating sphere is not there, then you cannot analyze this sample. Then third one is called an opaque liquid. Opaque liquid means very highly colored sample. A sample which is highly dark color, dark red sample, dark blue sample, dark green sample, that means practically light cannot pass through the sample. It's totally opaque. In that case, again, you have to use an integrating sphere, and you can make only reflectance studies in this case. Not transmittance, only reflectance using an integrating sphere. That's an opaque liquid. So depending upon the type of liquid, whether it's a transparent liquid, is a translucent liquid, or a turbid liquid, or an opaque liquid, sometimes you may require an attachment, an accessory that is to be used along with the UV spectrophotometer. Similarly, coming to solids, solid can be a powder solid. It's a pharmaceutical drug. It's a coating on it. It can be a mirrored surface. It can be a spectacle. It can be a lens, or it can be a mirror. A solid sample. Then again, you have to use either an integrating sphere, or there is another attachment known as specular reflectance attachment. You use one of these, and then you have to measure only the reflectance study. You have to you have to do only the reflectance study of solid material. No transmission method, no transmission study. Only reflectance is possible for solid. But you should have the attachment, and that is to be used along with the UV spectrophotometer. Reflectance applications, color analysis, as I told you, we have got a separate color measurement system, color analysis, reflectance properties of coatings on architectural glass. Even suppose I am using a spectacle. Now on my spectacle, suppose there's a coating, anti-reflectance coating. I can study the coating on my glass, on my spectacle. How effective is that coating? I mean, that can be, I can study the reflectance properties of that coating using a UV. Only thing I should have an accessory for that. Physical characteristic of mirrors and chemical composition of a powder. So all these are done normally by reflectance analysis. And when you say reflectance, I'm not going into details. There are 3 different types of reflectance. One is known as specular reflectance, relative specular reflectance, absolute reflectance, diffuse reflectance. There are different types of reflectance. And for studying all these different types of reflectance, we have different types of accessories also. Okay, let us not go into those details. And what is meant by specular reflectance? It is yes, suppose you should have a very smooth surface, very smooth and even surface. When the light is falling on that surface, the light is getting reflected. Okay, in that case, your angle of incidence is exactly equal to angle of reflection. And then it is known as a specular reflectance. So specular reflectance is the reflectance wherein the angle of incidence is exactly equal to angle of reflection. But your surface should be very smooth, very even, shining and polished, then only specular reflectance will take place. Otherwise, what is taking place is diffuse reflectance. Suppose your surface is a very rough surface. It's an uneven surface. It's a powder sample. It's a structured surface. Then your diffuse reflectance will take place. In the case of diffuse reflectance, the light will go inside the material, and while coming out, it comes out in different directions. Then it's called a diffuse reflectance. And for diffuse reflectance, you should have an integrating sphere. Without a integrating sphere, you cannot measure a diffuse reflectance in UV. And selection of wavelength, of course, I told you, any quantitative analysis, you have to make the measurement at lambda max value. Lambda max means the wavelength at which maximum absorption is taking place. Suppose you have got a drug, it may be absorbing in multiple wavelengths, but at one particular wavelength, the absorbance will be going to the maximum value, and that wavelength is known as the lambda max value. And that lambda max you have to use for your quantitative analysis. Then your analysis will be accurate and very, very sensitive also. Okay. Sometimes even chemical reaction and complexation can increase the sensitivity of your analysis. For example, I can show an example. Is an inorganic analysis, iron and nickel. Okay, so suppose somebody wants to find out the nickel content in a solution where iron is also there. Okay, you have to use certain reagents. Directly, iron and nickel will not absorb UV. Certain reagents are required. So now, if you look at the first left-hand side spectrum, nickel sensitivity is very poor, and not only that, their lambda max also are very coming close to that of iron. So probably it will not be a very sensitive analysis. Now, what we are going to do, we are going to have a chemical reaction where we are going to add dimethyl glyoxame reagent, and dimethyl glyoxame will react with only nickel. It has got a selective reaction with nickel. It will not react with iron, and it forms a nickel complex. This dimethyl glyoxame will react nickel and forms a complex. And you can see the complex has got very high absorption value. Absorbance value is very high, and then there is a clear-cut difference in the lambda max value between this complex and that of iron. So you can selectively determine nickel by this method. It's not a complexation reaction, complexation method. There are these type of analysis. I think I will show you one slide coming after this. Basically, which is used in the determination of metallic elements and non-metallic elements in wastewater. And there we are using this principle of complexation. Analysis of absorbing samples. The sample is absorbing directly in the UV region. There is no problem. You can directly keep the sample compartment. You don't require. You may not require even any attachment. The sample will be containing chromophores, and then you can make a direct absorption measurement in the UV. No problem. Okay, but if the sample is non-absorbing, you got a sample, but the sample is not absorbing UV, but at the same time you want to analyze the sample for certain parameter. In that case, what will happen? non-absorbing sample, for example, applicable to water analysis. Why we are taking this is, suppose if you go to big industrial houses like petrochemical companies or fertilizer companies, even this steam, the power generation companies like Tata Power and all. I'm just giving an example. Power generation, they'll be using a lot of amount of water for boilers, steam generation, because the steam is required in their plant. So huge boilers will be there, and they are using water and converting this water into steam, and this steam is actually sent to the chemical process plant. So steam generation, they are using a lot of water. Now, depending upon the quality of water, that water may contain some metallic elements or non-metallic elements, and these type of water, if they are using without any monitoring, inside the boiler there will be a lot of scale formation, what we normally known as crust formation. And if this is not taken care of, sometimes it can even result in a huge explosion of the boiler. So it's a safety hazard. And similarly, they are using water in cooling towers. Okay, so the cooling tower, the water is to be, the heat is to be taken out. So those water which are used in cooling tower, water that is used in boiler houses, they are to be constantly monitored for different types of metallic and non-metallic elements. Okay, so now, for example, water contains iron, copper, or nickel. This type of metallic elements, or it can contain carbonate, it can contain phosphates, it can contain chlorides. And so they have to monitor the water for these type of metallic and non-metallic elements. At the same time, all these metallic elements will not be having a direct UV absorption. So what we do, we use the same complexometric reaction. So we have a certain model of UV which we are promoting in these type of industries, and it's a very specific model which is designed for water analysis. And for these metallic elements and non-metallic elements, we are providing different types of selective reagents. For example, if I want to find out iron content in water, there is a reagent called 110 phenanthrolene. And 110 phenanthrolene is a reagent which will react only with iron and form a complex which has got a UV absorbance characteristic. So from the UV absorbance of that complex, we can calculate what is the content of iron in water. Similarly, determination of cadmium, chromium, the magnesium, we can use diphenyl carbazide as a reagent. And so the different types of reagents are available. These reagents are also, will be provided along with the equipment. And there is a certain method which is everything is inbuilt. So you can actually quantify non-absorbing samples also. Otherwise, if I want to find out iron content or cadmium content or chromium content in water, I have to go to atomic absorption. Atomic absorption is a much costlier equipment. It has got much very high costly equipment. At the same time, you are getting UV for a very cheap price, and you can make use of this provision, non-absorbing samples by complexation reaction, where we are providing reagents for metallic and non-metallic elements. These are selective reagents. They will select with only the designated metal or non-metal and form a complex, and then we should be having UV absorption, and you can actually quantify the content of metal or non-metal. Then I told you about the last, this thing is your single beam equipment and double beam equipment. I told you the students also should understand what is meant by a single beam equipment and double beam equipment. Whatever instrument you are using in a laboratory is a double beam equipment. The single beam equipment, we have a source of light. We have a monochromator, because the polychromatic light is to be converted to monochromatic light. Then it will pass through sample compartment and directly go to detector. And whatever the signal that is coming, the detector will be processed by the signal processor, that is a PC. So you have to, there is only one, what you call, so this is a single beam equipment. So you have to initially do the measurement with the reference, then remove the measurement, remove the reference and keep your sample and repeat the experiment to find out. Whereas in the case of double beam, you can see the source, monochromator, and whatever is coming out of the monochromator is split into two different beams. One beam is passing through reference and another beam is passing through sample simultaneously. Whereas in the case of single beam, it is one at a time, reference and then sample. Here it is reference and sample simultaneously, the light is passing through, and then whatever is coming from the reference side and sample side, either they can pass through two different detectors, or we can combine these two beams and pass to single detector, and then the signal can be processed. Okay, there will be ratioing, reference and sample signal ratioing, and then you can calculate. But what is the advantage and disadvantage of this? Okay, advantage of double beam system. Today, everyone wants a double beam system only. Today, whatever you are having in your lab is also a double beam system. Today, nobody wants a single beam system. Single beam system advantage is high energy throughput, very few moving parts and less expensive. Cost is very low. At the same time, disadvantage is very unstable and no reference correction. Suppose if there is some variation in the voltage when you are making the measurement of the reference and then later it's sampled, that will affect the reading. So very unstable and no reference correction, that's a major disadvantage. While coming to double beam systems, advantages, more sensitive, more stable, and if at all any fluctuations are there, there will be automatic correction. And disadvantages, more electronics and moving parts, and cost also will be slightly more. But that cost is justified because you are getting a much more sensitive system. You are getting a much more stable system. Okay. And the last slide is a very important accessories. I'm just showing that I'm not going into the details. There are different types of accessories available for UV. Long path length rectangular cell. Suppose your sample has got very, very low concentration. And everyone knows now, please keep in mind your Beer-Lambert's law, absorbance is directly proportional to concentration. Now, in this case, you have got a sample where concentration is very low. That means your absorbance is going to be very low because in direct proportion, absorbance is going to be extremely low. So when the absorbance is extremely low, your quantitative results may not be perfectly correct. Okay, somehow you have to increase the absorbance value. Your absorbance value, as I told you earlier, between 0.3 and 0.8 for a normal analysis. So here the absorbance is much below that. So you have to increase the absorbance. For increase the absorbance, you have to increase the concentration. But unfortunately, in your sample, you just cannot increase the concentration. The concentration is only that much. You cannot increase it. Then what is the way by which you can increase the absorbance? And remember the Lambert's law, absorbance is also directly proportional to the path length. So in this case, if for such a sample where the concentration is extremely low, if I can increase the path length, I can increase the absorbance, and then I can have a very sensitive analysis. So different path length cells are available. 1 centimeter is the standard one, and there are multiple path length, different path length cells are available for different types of applications of these type of samples. Constant temperature cell holder, some of the biological applications, especially when you talk about DNA, RNA, and protein analysis, all those, they are all temperature sensitive. Temperature in the sample compartment should be constant. You have to, sometimes for DNA and DNA measurements and all, you have to hold the temperature at a constant value without any variation. Even slight variation in the temperature will affect the result. So there are different ways by which you can hold the temperature constant. By constant temperature cell holder is available, or you can even do by Peltier cooling and heating. Thermoelectrical temperature control cell holders are available, which are TCC 100, where you can actually electronically control the temperature so that the temperature remains absolutely constant. Okay, so these are all accessories. And then we have different types of integrating spheres. I told you for integrating spheres, for turbid samples and solid samples, you'll have to use an integrating sphere, and then you have to make either a transmittance measurement or a reflectance measurement. So there are different types of integrating spheres available for different types of different models of UV. So, and then TMS PC is also an attachment for DNA RNA quantification. is a purely biotechnological application accessory. And it also comes, I have told you about the importance of TM measurement, melting temperature of the nucleic acid measurement. So this accessory is used for that. TMS-PC is basically used for the measurement of melting temperature of nucleic acids, where you get a lot of information about the structure of DNA molecules. And this comes along with a special software which is known as a TM software. So these are some of the important accessories. A lot of other accessories also available for UV for different types of applications. I'm not going into those details. And then the last slide is do's and don'ts. I can just tell you, one major mistake many times people do in industry also, the drying of the cuvette. Once you use the cuvette for so many different samples, you have to, many times you have to clean the cuvette. Suppose you see some permanent, something is sticking inside. You have to use with a suitable solvent. You have to clean the cuvette, and finally you have to use rinse with the distilled water and then dry it. Okay. Now for drying, many times I've seen in industry people drying the cuvette in an oven. That is a wrong practice. Never do that. Because if you are trying to dry the cuvette in an oven, there can be very minute thermal expansion of the material, which will affect the path length of the cell, and that will affect your quantitative analysis. So never dry the cuvette in an oven. Rinse it with water, rinse with acetone, just keep it on your table. In 5 minutes time, the cuvette will be totally dry. Normal air drying. Never dry the cuvette in an oven. That's a major mistake. Second mistake, and then second thing, when you have to be very careful about the cleaning of the cuvette also. Because I told you, after so many samples, sometimes you may see something, some stain inside the cuvette and all. Sometimes it may not even go with a solvent. In that case, what you can do, one day evening, you can make a dilute chromic acid solution and dip the cuvette overnight in dilute chromic acid. Sometimes even you can dilute nitric acid. Nitric acid is also a very strong oxidizing agent. You can dip it overnight. Next day morning, when you come, you take it out, wash with plenty of tap water, then rinse with plenty of distilled water, and finally rinse with pure quality acetone and keep it on the table, dry for 2-3 minutes. Your cuvette will be perfectly okay. It will be perfectly clean. So that is that's another important thing. And the third one you have to be very careful is while filling the cuvette with a sample solution. I have seen people in industry also fill in the cuvette full, and then it starts overflowing. And when it starts overflowing, I have seen many industrial laboratories have seen people, how do they clean the cuvette? You are all wearing a apron. You are having a lab coat. Lab coat is made of cotton. And when there is a spillover, when there is something is overflowing, something is sticking, they take the end, they use the lab coat for cleaning the cuvette. They take the end of the apron and just clean it. That's also a very wrong practice, because your lab coat is made of hard cotton. And when if you are rubbing and cleaning the cuvette, the transparent side with your lab coat, many times micro scratches will come on the surface. Probably you may not be even able to see that. It's a micro scratch. But if there is a micro scratch, from there, the light will start scattering. Scattering of light will take place. That means the amount of energy passing through the sample and falling on the detector will reduce. That means your sensitivity will reduce. So never do that. So your cuvette is normally, I think, approximately 3 ml is the total volume. You can fill the cuvette approximately around 75% of the total volume. That's more than sufficient. And if something is sticking to the transparent side, take a very clean and smooth tissue paper, just wipe it once or twice. That's all. Then you can keep it inside the sample compartment and make the measurement. End of the day, take out the cuvette, clean it, dry it, and keep in. There's a box always coming along the cuvette, and then you have to keep in the box. Last one, another important thing which I want to tell is that when you are buying a cuvette, you will get a box, and the box there will be always 2 cuvettes. They will always come as 2 cuvettes will be there in one box. It is known as a matched pair. Suppose by mistake, by any chance, suppose one cuvette is fallen down and broken, another cuvette is still there. So you will again order for a cuvette. You will get a box, and that box also will contain two. So I have seen people taking one from the new set and one old one they will use, and they use it for measurement. Again, it's a wrong practice because they are two different batches. The cell geometry will not match. So never mix an old cuvette and a new cuvette. When you are getting a new cuvette, there are again two inside, and those two should be used simultaneously. Because otherwise the cell geometry will not match. The path length can be slightly different. That will affect your quantitative analytical result. So if one cuvette is broken, remove the other one also and go for a new set and then use those two cuvettes simultaneously. And then relative humidity should be around 15% to 60%, and room temperature should not exceed. Normally, ideally, the room lab has to be ideal condition. It should be an air conditioned lab. No dust should come on the instrument, and preferably if you can put a cover on the equipment at the end of the day, it's well and good. No dust formation will take place, because for any electronic equipment, dust is a major enemy. Dust formation should not take place. You have to take care of that, and you should have a stable electrical supply. Variation should not come. So these are some of the preliminary things you have to take care of. And when you start the instrument in the morning, suppose you are starting the instrument, see that nothing is there inside. Nothing is there in the sample compartment. Suppose cuvette is there, you please remove that. Okay. When the initialization is going on, nothing should remain inside, and the initialization will take a few minutes, and then it will be ready, and then after that you can start them. And normally, before making any measurement, it is always better to take a baseline correction. See the baseline. Auto zero you can do. If you are doing a photometric method, please make an auto zero. See that your absorbance is 0.00, and then you make the sample measurement. So these are the simple things we have to observe while working with a UV in the laboratory. And I think that is my last slide. Exactly 4 o'clock I am able to finish. So if there is any query, somebody can ask me, I will be able to answer. Amol is there? Amol? Hello? Hello?
Hello? Hello?
Amol has joined?
No, sir. No, sir.
Okay.
Amol sir is not.
Okay. Sir, any student has got any question, you can just read it, sir. I can answer that.
Very nice, sir. Thank you, sir. Number of 3 questions posted in the chat box. I will show you on the screen. I will show you on the screen.
Okay.
Can you see this, sir?
Sir, no, it's not visible, sir. If you can read it out, it is better.
How can we analyze UV inactive compounds on HPLC using UV detector? How can we analyze?
How can we analyze?
Analyze UV inactive compounds on HPLC using UV detector.
Okay. UV inactive compound, no sir, UV inactive compound.
Yes.
Sample is a UV inactive compound. You cannot analyze that on HPLC using UV detector, because if you want to use a UV detector, the sample has to be UV absorbing. Otherwise, there is a possibility you can carry out a post-column derivatization. There is something called post-column derivatization. When the compound is coming out of the column, it is to be derivatized with a certain reagent, and then after derivatization, the sample will become UV absorbing. Then you can use it with the UV detector. So if the sample is inactive, you have to use a post-column derivatization technique. Then you can analyze. Otherwise, no.
Okay. Then second one question, sir. In UV, why Lambert's law not obeyed for high and low concentration solutions?
Okay.
Why Lambert's and Beer's law for the high
See, more important is high concentration. Low concentration, your absorbance is going to be very low. So probably you'll not be able to measure the absorbance properly because sometimes your even noise level also can interfere. So it may not be proper. But more important is your concentration. If it is more than a high concentration, if you are going to use in UV, whatever absorbance reading you are going to get will lie in the non-linear part of the equipment. Every instrument has got a linear part, whether it is GC or FTIR or GC or LC. There is a linear part of the detector. Okay, so when you are making a measurements, your measurement should lie in the linear part of the curve. At very higher concentration, these points, these values will lie in the non-linear part of the equipment. And if it is lying in the non-linear part, using that absorbance value, if you calculate the concentration, it will be wrong. That is why we have to precisely control the concentration of the sample. So that all the readings what we are getting, it should lie in the linear part of the graph.
Yes. Okay, one more question, sir.
Yeah.
Why the same compound shows different lambda max as the solvent varies?
So what is the what one second, sir?
Same compound.
Ah.
Same compound shows different lambda max as the solvent. Solvent as different.
If the student, if he remembers whatever I showed you, the 4 different effects like hypochromic, hypochromic, and betachromic and hypochromic. Okay. Something what happens when you are using a solvent, this solvent actually, because of solvent effect, there will be a shift in the lambda max. So sample is same, but in a certain different solvent, the lambda max will change because of the betachromic effect, or which is known as a red shift or a blue shift.
Yes.
That is basically because of either red shift or blue shift. That is hypsochromic or betachromic shift.
Okay. Yes.
Any other questions, sir?
No, sir. Yes, one more question, sir.
Yeah, please, sir. No problem. No problem.
If the compound is chiral,
Ah,
then
okay.
for first question, what is the effect of derivatization?
See, chiral is something. Chiral will not chiral compounds will not affect the derivatization product. See,
Yes.
what are basically chiral compounds? They are basically your mirror images. Okay. So
Oh, yes.
chiral compounds, but normally when you are derivatizing, the UV absorption will not change. UV, there will not be any effect on the UV absorption characteristics of the compound, whether it's chiral. Only when you go for a chromatographic separation, your chiral compounds, you have to use certain different types of chiral columns for separating, otherwise you will not be able to separate. As far as UV absorption is concerned, once you derivatize, there will be no absolutely no effect.
Okay. Yes.
Any more questions, sir?
Yes, sir. Complete, sir. Okay. No more question.
So I hope I was able to give some basic information about UV to the students, and I
Yes.
hope it was quite informative for the students. I mean, I'll be happy if they have at least understood what basics I've explained and some of the important applications. And tomorrow again we'll have a very interesting discussion on FTIR and some
Yes.
of the interesting applications in pharmaceutical industry. So, if no more questions are coming, sir, I think then we can hold the session. We can.
No one, sir. No one right now.
Okay.
Okay. Okay.
Okay, sir.
Okay.
So
Thank you,
okay, then
sir.
I will
Thank
log
you.
out, sir, and tomorrow same time, I can use the same link.
Same time.
And the link is also same, no, sir? Link is same.
Link is different, sir. I will create and I will send to you.
Actually, link is going to be different.
Yes, sir.
Okay, then please make it and send it to me, sir.
Yes. I will
Either
send
by
to you.
today or tomorrow morning, you please send the link so that I can.
Today I will send to you right now.
Okay, sir. Okay. Thank you so much, sir. Thank you so much. Okay.
Thank you,
So
sir.
thank all the participants. Thank you very much for your attention. You are all with me for last 2 hours, and thank you once again. I hope you have benefited from this. And I wish you all the best and see you all tomorrow afternoon 2 o'clock. Okay. Thank you.
Thank you, sir. Good.
Thank you. Thank you, sir.